Okay, good morning, everyone. My name is Dashiell, and my project will be on the production of 3D printed forearm molds for superficial brachytherapy. My supervisors are Pejman Roshanfarzad of UWA Medical Physics, and very recently Luke Slamer of Radiation Oncology at Sir Charles Gardner Hospital. So I just want to jump in for a quick introduction on skin cancer. It is one of the most common forms of cancers, particularly non-melanoma skin cancers, which in Australia accounts for more cases diagnosed than all other cancers combined, with, in particular, basal cell carcinomas and squamous cell carcinomas. The incidence trends of non-melanoma skin cancers are on the rise in Australia, with a 39% increase in hospitalizations for non-melanoma skin cancers between 2002 and 2013. However, there's not more recent data, as it's not required by law to report these due to the number of incidences. The significance of skin cancer in Australia can be provided with the statistic of 2 of 3 Australians will have some form of skin cancer by 75, making it an important public health concern. To just start off with brachytherapy, it's a form of short-distance radiotherapy in which the radioactive source used is placed within or on the area being treated. It is a useful treatment method when external beam radiotherapy, surgery, and electron therapy are not suitable for the patient due to the location of the cancer. Superficial brachytherapy is often treatment for skin cancer due to the ability for precise dose delivery to the treatment site, while limiting exposure to surrounding tissue due to the dose fall-off. More recently, the breakthrough of 3D printing in medicine has allowed novel techniques to be implemented in medical physics and specifically in brachytherapy. It has allowed the production of patient-specific custom applicators to conform to unique anatomical topography from imaging data. These type of applicators can provide numerous benefits over traditional applicators in clinical practice. So to start off, we'll look at the actual traditional applicators used before this introduction of 3D printed applicators. We'll start with the surface mold applicator that was developed to provide a solid and reproducible holder of the source applicators for improved positioning within the tumor site. The advantages of this one was flexibility in the positioning of the tumor, and it allows an ease of producing for smooth bodily surfaces and uneven bodily surfaces. These molds tend to be made from wax, acrylic resin, thermoplastic materials, and gypsum. When surface molds are not necessary, surface flaps are used for flat surfaces. These applicators are made from a silicon-based material and are formed into tubes or pellets that house the catheters for the radioactive source. These are used in larger tumor volumes and regular surface to maintain a conformal dose distribution. These also were made by Elector in conjunction with radionuclide shielded applicators. These are metal domed applicators in which the metal rod of the source sits inside. These are usually used for small tumors. The shielding property of these applicators are they are made of tungsten, providing effective shielding against the high dose rate source located at the top of the applicator. And lastly, the electronic shielded applicators were implemented into clinical use to reduce treatment time and dependence on high dose rate brachytherapy techniques. These can be intracavity or superficial applicators that deploy the radiation, which happens to be an X-ray rather than a radioactive source. For my project, the overarching aim is to create a 3D printed forearm brachytherapy applicator, but I've broken this into a couple of research aims. The first is to construct a suitable 3D printed forearm applicator, phantom, which will be used for the dosimetry segment of this project. Further from this, we need to design and print the relevant forearm applicator that fits to this phantom and can be used in the mock simulated brachytherapy sessions in which we can gather the dose data and compare with the brachytherapy treatment planning system. The method for the phantom will first be gathering laser and CT scan data. This will be old patient CT scans from which we will take the parts of the bones and put it into my own forearm scan. These DICOM files will need to be converted to STL files, which will be used for 3D printers. When printing this phantom, PLA will be an effective filament for regular tissue, but stone fill will most likely be the filament used for bone, as it has a higher density and more likened to bone. Prior to printing, though, in the rendering of the phantom, we need to include cavities for TLDs to be inserted within for these dose measurements. And finally, once the printing has finished, we will laser cut cross-sectional slices to insert film for more aspects of dosimetry. The methods of printing the applicator will be another scan from which we'll get the anatomical topography for the inside of the applicator. Once scanned, Mesh Mixer and Autodesk Fusion 360 will be used for image processing and inserting the catheters into the applicator model. This applicator will then be printed using the bamboo X1 carbons that we have at the Sir Charles Gardner Hospital. And finally, we need to ensure that the applicator fits correctly to the phantom. Finally, the dosimetry aspect of this project will be to construct a mock treatment plan to gather dose data. We need to first cut the film that will be inserted into those cross-sectional slices and insert the TLDs into these cavities that we have created. We'll undergo the mock treatment to gather this data, and then we will create dose distributions from the TLD and film dose data using Film QA Pro and other dose distribution software. The final step of this will be comparing this to the treatment planning system used in brachytherapy to create differences or similarities between what we've predicted and what we've observed. This is my progression plan for next year, in which I start in February, but I've taken time over the holidays to make sure I'm adequate with the software and the printing to be able to ensure I can do this project correctly. I've been a little bit conservative with the time just so I can prepare writing my thesis, but also giving myself extra time in case things fall behind schedule a little bit. So the benefits of the 3D applicator, the main one is the ability to match the topography of the skin surface, which will help with dose distribution over the skin. These applicators provide superior dose distribution that conform well to the treatment plans and even spare dose at organs to the organs at risk surrounding the planned target volume. The ability to precisely place the catheters while the applicator fits well to the skin in providing this dose distribution can reduce air gaps, which otherwise will change the dose distribution compared to the treatment planning system. These applicators are very reproducible and you can change them very easily in the clinical setting if the skin or the tumor change in shape. The main challenges that I think I'll come across in this project will be the applicator positioning, the phantom bone printing, radiation exposure, and time and financial constraints. The forearm doesn't have very many distinguishable anatomical features, and so the process by fitting the applicator to the correct area will be a tough challenge, but the thought of process right now between Pejman and myself is extending the print at a lower infill percentage down to the wrist or up to the elbow to create this distinguishing feature that can allow for the correct placement. The bone printing for the phantom will also be a problem, as stone fill is a very expensive filament and we don't want to waste this at all. And so we need to investigate the best mimic of the bone, which can look at different infill percentages or different filaments for different parts of the bone, comparing compact and the less compact areas. In the mock treatments, there will be some level of radiation exposure, although not much, but the radionuclide handling course that I'll be taking over the summer will provide adequate knowledge and safety for these processes. And the time and financial constraints, over the summer I'll be spending time getting used to the printing software and the other software for 3D rendering to make sure I can do this time effectively and not waste filament. There's 3 publications that I found extremely useful when looking at the literature review. First was Casey et al., which is a clinical trial of a basal cell carcinoma on the anterior shin, which compared to all the other papers that I looked through is the closest body part to a forearm. They underwent an aquaplast mold first, but opted for a 3D printed mold instead to get rid of the air gaps that formed. This shows the effective reproducibility of these applicators, as well as reducing air gaps to provide better dose distributions. The clinical trial was a success, and there was a full eradication of the basal cell carcinoma. Later et al. Showcased easy reproducibility in applicator production and effective treatment, and also differentiating treatment planning with different CT scan HU value windows that showcased air gaps at some values and some that didn't. And finally, the most important publication, in my opinion, is a financial review conducted by Arenas et al. They went through the process of the conventional gypsum mold production compared to a novel 3D printing mold production. We can see from here the waiting time for the conventional process was 72 hours due to 2 CT scans and the setting of the gypsum mold, while the 3D printing only accounted for the 3D printing and the CT, one CT, which is a total of 31 hours. The labor cost in the conventional process had much more steps, which resulted in 211 euros compared to the 152 euros for the 3D printing process. And finally, the material cost for the conventional process was 318 euros due to the 2 use of CTs compared to the 158 euros for the 3D printing process, which only accounted for 1 CT and the mold filament. We can see that from these, there are definite reductions in costs that can provide excellent reduction in cost and labor. This is the summary table from my literature review that provides softwares, treatment planning systems, filaments, and printers that can all provide excellent information for me in the processes that I can take with my project. The use of 3D printers in the advancement of superficial brachytherapy is a novel idea that has promising outcomes. While traditional applicators provide adequate results, clinical trials and research have provided new information regarding the improvement of these by utilizing 3D printed applicators. This comes from the financial cost and labor reduction in an otherwise expensive and labor-intensive area of radiation therapy. The promising nature of 3D printed surface applicators can be further consolidated with future studies to improve the therapeutic ratio and patient comfortability. This project, of course, does not come without an associated cost. I've been informed by Pejman that the cost will be upwards of $500 for filaments and machine parts. This will be supplied by UWA, and the equipment will be supplied by Sir Charles Gardner Hospital, which I'd also like to offer my thanks to, as this project would not be possible without it. There is also an ethical consideration with the use of patient CT data, which would need to be approved in the production of the Phantom. These are my references, and I'd just like to make a few acknowledgements. First, to Pejman for his insight and knowledge, which has helped me enormously in the writing of my proposal and literature review, and also Luke and Mashid for allowing me to attend the Brachy QA sessions, which really furthered my knowledge in this area when we had not covered it in class yet. So thank you very much.
Excellent. Thanks, Dashiell. Great presentation.
Thank you.
We'll open up to questions now. And Mashid.
Thank you, Dashiell. That was very nice. And you're very welcome. You are more than welcome to join us for QAs or observations anytime you like. Just let us know if you need to come over more. So I have a few questions. One is the applicator that you're using for this technique. Is it going to be the same applicator type as we are currently using for skin treatments?
Do you mean surface mold or as in 3D printing?
No, the applicator itself, because there are different types of applicators. Is it going to be the same ones, or is it going to be a different type?
I'm a little bit unsure. I think I've seen the 3D printing for different areas of the body, which I will try and take the inspiration from then to create this, but I haven't seen the surface mold ones for forearms just yet. So
that's okay.
I'm sure that we'll use 3D printing and try and replicate as best the forearm ones that are currently in use.
Okay, sure. Because yeah, there is a variety of applicators that could be used, and you will need to know exactly which ones would be suitable for this type of treatment.
Yeah.
Then the other thing you mentioned is the bones, and why is it important to consider and focus on those two bones in these treatments?
So for the forearms, the bone is the most radiosensitive part. And so reducing or knowing the dose of the bones will provide us with information on how much this will target the bones, which we want to reduce, of course.
Right. So does it have anything to do with the energies that are used in Brachy, I think?
I'm actually unsure about that. Sorry.
It's something to
I'm
think about. No, that's all
yeah,
right.
definitely
That's all right. It's something to think about. You're just starting this. Like the purpose of these questions is to kind of give you a direction to think about it differently from an aspect that may not have been thought about before. Then
Yeah, no, I'll note that down.
all right. So then on slide 13, can you go back for me, please?
Yeah.
Okay, so you see you mentioned the difference in the costs, but I think something is missing on the table on the right, and I understand you have taken it from somewhere.
Yes.
But what happens when you 3D print the mold? There is a kind of detailed QA process that they have to do on the mold to make sure that it is suitable and it's like perfect for the purpose. We have to CT it separately before it goes on the patient. We have to,
Yeah.
that process and the time and the human cost, I don't think is mentioned here. So that is something to think about when you are doing your work, because it's missing here.
So you're saying that their process of 3D printing will be different to our hospital's one and may incur a slightly higher waiting time and
No,
human cost.
that's not what I mean.
Okay.
The cost, like you see, there is stage 4, like the phase 4 says 3D printing of the mold with guide tubes, and then it goes straight to the CT of the mold on the patient. But that's not what happens in reality. So you need to do QA on patient-specific created molds so that you make sure that like there's not an cavity, for example, inside the mold, or there is like a detailed process for QAing of the mold, and so that bit is not mentioned here. All right. Okay.
Thank you, Mashid. Godfrey, do you have a question?
Hi, thank you very much for the good presentation and kind of clear thought. I just wanted to ask you, you're going to do some plans in the TPS or brachytherapy treatment planning system.
Yes.
I'm wondering which algorithm are you going to use? Are you going to use the model-based or you're going to use TG43?
I think I had a thought about this the other day. Is obviously the treatment planning systems use, or the one for brachytherapy uses TG43, which is assumes all water. So that's a thought that I had, is either I do a comparison between what will, like the difference between the dose distribution in TG43 and the dose distribution that I will encounter with the treatment, or the other treatment planning systems which don't assume this and do a similarity comparison. So I'm unsure yet of which I will take, but one of the two, either a similarity or a difference comparison between the two.
Yeah, the system, you can actually do a model-based as well. So yeah, it's worthwhile giving it a go. Otherwise, the TG43 doesn't give you much.
Yeah, of course.
Yep. Okay.
Thank you.
Thanks, Godfrey. Roger?
Dashiell, a very nice presentation, and thank you. I've just got a very quick question. It's concerning the work of Arena Sadal, the slide that's up at the moment. Was that purely a financial analysis? I mean, the difference in human application, human cost seems to be more important than the difference in the actual material cost to me. I mean, compared to the total cost of a treatment, it must be a fairly small component. So I guess my question is, did they go forward and look at the therapeutic outcomes with the two different methods, or was it purely a desktop audit of the costs?
Yeah, if I remember correctly, it was a purely financial review of clinical workflow that they calculated these differences and also did a rough estimation on how much a single 3D printed applicator will cost.
Okay, thank you.
Thank you.
Excellent. Thanks, Roger. Just one more question, Ashleisha.
Yeah, thanks. Thanks, Dashiell, for the presentation. So regarding the 3D printing of the cast, previously I printed a cast for the forearm as well, which was for a different purpose. So what I observed was that it mostly it will tend to like fit loosely rather than tightly if you are using like the laser scan. It's
Right,
just based on how it works. So that's just something to note.
Sure, yeah.
We did use sort of like something to tighten it up later, so which worked partially. But yeah, so if you need any help with designing that, I'm happy to discuss that later.
Cool, thank you very much. Yes, I'll definitely look
Yep.
into that if that's the case with the laser scans.
Yep, no worries.
Thank you.
Thanks, Ashleisha. Thanks, everyone, for the questions, and great work, Dashiell.
Thank you.
All right.